Your application hits hypergrowth. Traffic spikes, logs flood in, and the database behind the scenes begins to struggle under the weight of data packets. Traditional relational databases are designed to manage this growth by scaling vertically. You accommodate the new demand by buying a faster server with more throughput. Look at this vintage IBM mainframe. It represents the original logic of data management, putting all critical records inside one massive high-performance machine. But every machine has a physical limit. Eventually, you reach a point where no amount of extra RAM or CPU upgrades can keep pace with the incoming requests. Reaching the next level of growth requires moving toward a different setup, horizontal scaling across a network of smaller, coordinated machines. Standard relational databases give you absolute transaction integrity, but they rely on a single primary server to manage writes, creating a hardware bottleneck that can fail under heavy stress. Optimization and read replicas can extend the life of a central server, but the requirements of global traffic eventually force a move toward architectures that are distributed by design. This distributed approach is known as sharding. You take your massive dataset, break it into smaller pieces, and spread those pieces across several commodity servers. Sharding resolves the physical storage bottleneck by spreading the payload across multiple nodes, expanding far beyond a single disk. But while the storage problem is gone, you've introduced a coordination challenge. The network must now find the right data across a complex map. When data lives on dozens of different machines, the system has to have a way to know which server holds the most current and accurate record. To solve this, architects generally choose between two specific distributed network layouts: a single master topology like MongoDB or a masterless topology like Cassandra. This choice determines how your system handles pressure. You're deciding whether your growth will be limited by how fast one master can coordinate writes, or how well your application handles temporary data inconsistency. We can see the single master layout clearly in MongoDB's replica set architecture. In this setup, one primary node handles every incoming write. It then pushes copies of that data out to the secondary nodes. By routing everything through one primary node, the system ensures strong data consistency. There's no confusion about the state of a document because there's only one source of truth. The trade-off is that this primary node is a single point of failure. If it goes down, the entire write process stops, and incoming requests begin to pile up. To get back online, the secondary nodes must run an automated election to promote a new primary. Only after a winner is chosen can the system resume processing new data. During that election, your application is effectively unable to accept new writes. The single master approach gives you reliable consistency, but it leaves you vulnerable to these windows of unavailability when a node fails. On the side, we have masterless topologies, used by databases like Apache Cassandra and its decentralized gossip protocol. In this ring, every node is equal. There is no central master. Any node can accept a read or write request at any time. This allows for massive write speeds and zero downtime. However, it's possible for two different nodes to receive conflicting updates for the same record at the same time. Because the system is eventually consistent, you run the risk of reading stale data. To prevent this, the nodes must communicate with each other to compare timestamps and agree on the correct version. You manage this through tunable consistency, forcing a quorum vote that requires a majority of nodes to agree on a record before it's served. The price for that accuracy is network latency. Requiring a majority agreement on every operation takes more time than just trusting a single master. Masterless setups provide high availability and fast writes, but they shift the burden of managing data consistency to the developer. Choosing between these setups isn't about which database is better, it's about which set of trade-offs matches your application's requirements. There are formatting differences to consider too. MongoDB's BSON documents offer more flexibility for rapid development, while Cassandra's column families are optimized for massive sequential write speeds. We can use this framework to map out the right path based on where your specific bottleneck lies. If you need structural flexibility, handle a high volume of reads, and require data to be consistent the moment it's written, follow the single master path. This is the right fit for dynamic product catalogs or content management systems, where accurate data is the priority. If your priority is extreme write velocity, zero downtime, and writing data across global regions, the masterless path is the standard choice. Faster. You'll see this architecture in high-frequency sensor streams or global user logging systems, where the system simply cannot stop accepting data. Moving away from traditional relational databases means you lose the automated safety net of absolute ACID guarantees. Reaching a global scale always involves a sacrifice. Success depends on identifying the distributed architecture with the specific trade-offs you are best equipped to handle.